Mic check, check, check. Hello. Mic check. Mic check, 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 check. Hello. Mic check. Mic check. 1 2 3. Mic check. Hello. 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 Mic check. हाई फ्रिक्वेंसी ज्यादा है. हाई फ्रिक्वेंसी ज्यादा है. माइक चेक चेक चेक. हेलो. हेलो. माइक चेक 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 चेक. हेलो. हेलो. माइक चेक 1 2 3. माइक चेक. हेलो. 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 माइक चेक चेक चेक. हेलो. 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 माइक चेक. माइक चेक. माइक चेक 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 चेक. हेलो. माइक चेक. माइक चेक चेक. हेलो. हेलो. माइक चेक check check check. Hello. Hello. Mic testing 1 2 3. Mic check. Hello. 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 Mic testing 1 2 3. Hello. 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 हाई फ्रिक्वेंसी बहुत है. हेलो. 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 है. अभी भी है. हेलो. माइक चेक 1 2 3. माइक चेक. हाँ ठीक है. हेलो. माइक चेक 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 चेक. हेलो. माइक टेस्टिंग 1 2 3. माइक चेक. हेलो. 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 माइक चेक 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 चेक. हेलो. हेलो. माइक चेक. हेलो. 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 माइक टेस्टिंग. हेलो. हेलो. माइक चेक. हेलो. हेलो. माइक टेस्टिंग. हेलो. 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 माइक चेक. माइक चेक 1 2 3. माइक चेक 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 चेक. हेलो. 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 माइक चेक. Okay, so I should. Okay. Okay.
Good evening. Welcome to this public lecture at TIFR. My name is Anish Ghosh. I'm the Dean of Mathematics here. This week, we are very excited to be hosting a conference joined with the London Mathematical Society, whose president, Jens Markloff, is with us. Jens, say hello. And as part of this conference, we are very privileged to have with us Professor Martin Bridson, president of the Clay Mathematical Institute and also professor at Oxford. Before we start, I'd like to welcome the director of TIFR, Professor Jairam Chengalur, to say a few words.
Thank you, Professor Ghosh, and welcome everybody to this public talk, and welcome to TIFR, those of you who have come from outside. I'm truly delighted to be able to welcome you all for this public talk. Probably many of you have heard of TIFR, but let me just say a few things about this institute. It carries out fundamental research in a diverse range of topics: physics, chemistry, biology, mathematics, and computer science. And mathematics, particularly, the topic of today's talk, is something which was started at TIFR from the very beginning. So we've been doing mathematics at TIFR for more than 80 years. And in many of these areas, particularly mathematics, but also in other areas of physics, chemistry, biology, and so on, there are topics that we are researching on at TIFR where we are often one of the only, if not the only place in the country where such studies are being carried out. And so we've always regarded it as part of our mission to try and, disseminate this knowledge, try and communicate with other people. And we've done it at a variety of levels. In mathematics in particular, from the very early days, whenever we had distinguished visitors coming and giving courses at TIFR, these were brought out in the form of lecture notes distributed to universities around the country and also abroad, and they formed a very useful resource for mathematicians, not just students, but also mathematics researchers from all over the globe. That is a tradition, of course, we continue. We have the Center Director for the International Center for Theoretical Sciences with us today over here. And so ICTS has its mandate to carry out in a similar fashion workshops and in advanced topics in theoretical and also experimental sciences, where they try and seed new areas of research in the country. Once again, all of the material which is gathered during this workshop, particularly the pedagogical lectures, etc., are all available as a video archive. This is freely available on the internet, and it's one of the largest resources worldwide for many of the topics where ICTS has conducted schools. Another way in which we try and reach out and communicate to people about the work that happens here at TIFR, as well as exciting developments in the world of research in multiple fields happening all over the world, is through talks like this one, through public talks and engagement with public at different levels. So TIFR has had, again, from the very beginning, a very vibrant outreach program. It's one of the oldest in the country and also probably one of the largest in the country. So, for example, we have in rural Maharashtra built one of the largest radio telescopes in the world called the Giant Meter Wave Radio Telescope. And this public outreach program over there is probably one of the largest public outreach programs in the country, attracting tens of thousands of people. In all of our centers, we have regular public outreach programs. Here in Mumbai, we have a very long-standing series called Chai and Why, which is a public talk held at the Prithvi Theatre in Juhu every alternate Sunday, and every in the intermediate Sundays, it happens at Ruparel College, and for months on which we have 5 Sundays. On the 5th Sunday, we do a live cast from one of the labs over here. So for those of you who are interested in, just finding out what's happening in the world of research, please do connect to our Chai and Why program. Its details are freely available on all of the social media. Today, for this public talk, we are truly delighted to host a distinguished speaker, Professor Martin Bridson, the Whitehead Professor of Mathematics at Oxford, and as we also heard, the President of the Clay Institute. You will shortly hear a more formal introduction of the speaker, but I would like to take this opportunity to thank him for accepting our invitation to be here for both for the conference and more particularly to be here for the talk today. Thank you.
Thank you, Professor Changalu. I'd like to now ask my colleague, Professor Mahan Maharaj, to introduce Professor Bridson.
Right. So it's a delight. It's a real pleasure to be here to welcome Professor Martin Bridson, Whitehead Professor of Biomathematics at University of Oxford and the President of the Clay Math Institute. He's a fellow of the Royal Society and the American Mathematical Society, and he was an invited speaker at the ICM in 2006. There are a couple of things that I just wanted to say which are mathematical. So one of the topics is, I think, something he's talking about today, and another we hope to hear about tomorrow in the more specialized zone. And these are areas where he has contributed fundamentally over decades, and one of which is algorithmic problems in group theory. Groups are basically mathematical entities which encode symmetries of various objects, in this particular case, symmetries of some geometric object. And one asks questions of these, and whether they can be algorithmically decided or not. And he's going to be telling us more about it here. And there's another theme which I find particularly inspiring about Martin's work. Profinite rigidity is the name. It's basically asking whether groups, these things that encode symmetries, can be captured by their finite quotients or finite incarnations. And both these things have influenced the field tremendously over the years, and Martin's certainly a leading light in our area. There's another thing, which is his contribution to the larger mathematical community. It's this amazing book, which I wish I had when I was a grad student, joint with Hefliger, Metric Spaces of Non-Positive Curvature. It's influenced certainly, many students and people who have become mathematicians subsequently, and has also won the Steele Prize from the American Mathematical Society. So I'm delighted that Martin is here today. As you will see, he's a marvelous speaker in addition. And I'd like to invite my colleague, Professor Radhika Gupta, who's exactly in this area, to formally welcome Martin.
So thank you for all those kind words of welcome. It's a great pleasure to be here for this workshop between the London Mathematical Society and the Tatra Institute. But it's a great honor and a pleasure to be in TIFR. And it's been in my consciousness since I was a graduate student, on account partly of some of these great lecture notes that were mentioned, and also some of the great people who've been here and have and remain here. And so I've enjoyed all my previous trips to India, but this is the first time I've actually managed to get inside TIFR. And so it's really a great honor and a privilege to be here. Thank you. I usually say, and it's really true. So I'm an enormous cricket fan, you know, and I love coming to India for all sorts of reasons. But just the thought that I'm amongst a billion cricket lovers was just a fabulous thing that I find very inspiring. So I'm going to talk about the sort of things that Mahan was alluding to about groups and symmetries, and I'm going to try and do it. Not with, this is a public lecture, and it's very much meant to be a public lecture, and I hope I'll be able to communicate ideas to a wide audience. But I'm honestly going to talk about the sort of objects that really interest me, but obviously it'll be in a somewhat impressionistic way. But I've tried to choose things that have a visual appeal as well, so to try and convey the motivation behind these ideas. So I'm going to start off very generally and then get more specific. So very generally, why do we do mathematics? And we, in this context, I think, is our species, the human species. And somehow it's because I like to think it's because humans cannot abide not knowing something, right? In the end, we tell governments various things so that they will fund our research and so on. But in the end, what makes the individual want to do mathematics is just the same as any fundamental science or any fundamental knowledge. We just can't stand not knowing, right? Basically, curiosity, that you want to understand something. And that's sort of the basic premise of everything, well, everything I do, but everything I'm going to say today, right? We must know. We just can't abide not knowing. But there is great benefit to civilization from this. And there's various quotes of this, but I particularly like this picture of Roger Bacon, who's one of the early serious scholars in Oxford. He lived in Oxford in the 1200s. He who knows not mathematics cannot know the other sciences, nor the things of this world. I like that. Knowledge of this science prepares the mind and raises it up to a well-authenticated knowledge of all things. Okay, that's good. So yes, we do mathematics, so we must know, but there's also this thought that there's an honesty about mathematics, an engagement with the truth that we really want to get at. This is Plato. He's the guy on the left, who said similar things to Bacon much earlier, but he also had this inscription above the door of his academy in Athens, which roughly translates as "Let no one destitute of geometry enter here." And so that is the other theme, that in this craving for knowledge, at least if you have a certain mindset, there's always a craving for geometry, to see what's going on, to understand what the great picture is. So as been said, I'm at present Twain Mathematics Institute, it's a great honor, and I like, on the same theme, why CMI exists. So this is the statement that you'll find on our webpage: to further the beauty, power, and universality of mathematical thought. That's what we're trying to do. And I think all three words are important, right? Beauty is engaging, power for what we can do with mathematics, and also universality. It's an extremely important idea, I think. But we don't do mathematics. So we talk about Indian mathematics, meaning it's done by Indian mathematicians, but there's no such thing as Indian mathematics, right? The theorem doesn't stop being true when you get to the airport. Now, the universality of mathematics, the fact that it belongs to the whole of mankind, and also the way in which it encodes different phenomena from different settings and finds a single unifying truth in it. So universality in both of those senses. So how do we do, so we want to do mathematics, how do we do it? Well, roughly speaking, quoting Plato again, first of all, we look for models, right? We go and we find things in the world, and we see evidence of a phenomenon, we try to understand that phenomenon, and we abstract the, I just realized you're out of luck because I forgot to start my timer, which means that you're going to get more than you bargained for. We find evidence and examples of things in the world, and we ask, and it's a very fruitful process often, what is the essence of these problems? What is the common essence? Now, what is it that we're really studying when we see these classes of similar objects? We identify models or ideal forms of what we're seeing. We make definitions to encapsulate that essence. We abstract. And then, and this is what sets mathematics apart from other sciences, perhaps, proof, right? So, of course, all of science is interested in truth, but what really sets mathematics apart is proof, right? We really want to prove something, not just have overwhelming evidence that it's true, but look for proof that something is true. And we love structures. And what I particularly want to emphasize in the first part of this talk, which is, I think, something that the general public feel, those clever mathematicians, they do extremely abstract things, but then they know everything that can usefully be known. And you know that surely any problem I ask them, they'll be able to do if it's well posed. The fact that truly hard things are close at hand, I think, is not sufficiently widely appreciated. So I want to sort of give a couple of examples about how you come across truly hard things in very simple sounding settings. And then this idea of the unknown. You know, there's vast amounts of mathematics we know, but very quickly there are far greater masses of mathematics that we don't know. Things we don't know very quickly outnumber the things we do know. And I want to discuss this idea of the unknowable, or things that we know to be impossible. And again, it should be close at hand, not abstract. And I'm going to try and build a lot of this talk around groups, which we'll discuss in a minute, symmetry, but also knots, the first word in the title. Now, what's a knot? I really mean what you think I mean. You take a piece of string, you tie a knot in it, and then you fix the end. So it should be a closed knot like this. And one sees knots in all sorts of contexts, right? So you see it in art or architecture or tying up boats or whatever it may be. On the that's the emblem of the Clay Math Institute up there. That's the knot called the figure 8 knot. And then I rather like this picture. This is a genuine electron microscope picture of a knotted piece of DNA. Right? The knots occur all over the place in all sorts of contexts in science, art, and beyond. And so we could try and think about how we do the mathematics of knots. How do we go about understanding knots? Now, for example, the sort of thing I'm going to say is I could just tell you, and it's true, that the knot in the logo of the Clay Math Institute is the same knot as this. It's a famous knot. It's called the figure 8 knot because it's often drawn like that. But what do I mean when I say that that knot in the logo of the Clay Math Institute is the same as this picture of that knot? Well, this is us doing mathematics together, right? We have to decide what we mean by the same. Well, we probably mean that I can take hold of that knot and give it, well, the pointer is very subtle. I can take hold of that knot and I can drag that first strand up a bit and then turn it round and it will look like this one. So I mean, I can manipulate that knot, just move it around in three-dimensional space until it looks like that one. Okay? But now I've made an abstraction, right? I've said the knot is the same. I've made some commonality between those two pictures. And we're going to think about how we go about deciding which knots are the same and which knots are different. That's going to be part of the narrative we're trying to build. For example, I claim, and it's true, that these are the first few knots. Now you start asking yourself, well, can I start listing all the knots? Well, the easiest knot is the unknot or the not knot, which is that one up the top there. It's got, this is much harder than it looks. It's like some video game. That's got no crossings. That's the only knot you can draw that has 3 crossings. That's called the trefoil knot. And then the one I had, a figure 8 knot, I've just turned on its side. That's the only knot that has 4 crossings but can't be drawn with 3 crossings, and so on. And those are the first knots. Those are the knots up to 7 crossings. That's called a knot table. And the claim is that is a complete list of all the knots where you can draw a picture of it so that there are only at most 7 crossings. That's the first claim. Second claim, they're all different. Right? That I haven't made a mistake and drawn the same knot twice. That is to say, if I take 2, say I take that one, and I take that one, you can't take that one and manipulate it, pull it around until it looks like that one. So that's doing mathematics, right? That's doing it. First of all, we said what we mean by a knot, or what we mean for two knots to be the same, and then we started trying to classify them. So these pieces of string or pieces of art have become mathematical objects that we're manipulating. Right. So that's where we're going to go. We're going to talk about knots, but let's go back to this. How do we do mathematics? We seek ideal forms, abstraction, we're searching for proof. And I want to get at this idea of the hard and the unknowable being close at hand. So we're going to start with something easier, which is the first mathematics every child learns, the whole numbers, right? Just counting numbers. So somehow in every civilization, we have words for the act of counting small numbers. Since I'm in India, I ought to have started with 0, but I didn't. I started with 1. 0 being a more subtle thing, of course. We start counting 1, 2, 3, 4. And when you're a little child, you know, this is your first experience in mathematics. As a little child, you figure out that 2 chairs or 2 apples or 2 toy cars have something in common, this thing called 2, right? That we all are somehow programmed to be able to do this abstraction, to go from pairs to the commonality, the number 2, and give that a name. And what's the benefit of that abstraction? Well, then once you've got numbers, you can start manipulating them. Right? You can add them. So when somebody presents you with 4 apples and 3 apples, and you put them together and you know you have 7 apples, you don't have to count them again, right? You know that 3 plus 4 is 7. But the abstraction gives you a power to do other things. And so every culture has its counting numbers, and then it starts doing arithmetic. It starts adding and multiplying, and then it wants to divide, so it has fractions. And this is a great example of universality, right? So all human cultures do this, because when the aliens arrived from beyond the solar system, the first thing we want to know is, are they vegetarian? We hope so. But then we can start, what will we start discussing with them, right? They sadly won't know about cricket, so we have to find something else to talk about. They will know about arithmetic, right? There's no doubt that any alien civilization that arrives will know a certain amount of mathematics, and they will certainly know about arithmetic. It's somehow the most primitive mathematical structure that one being any intelligence, can think of. So let's go to this question of hardness. Well, if numbers have always been with us and have always been thought about, surely we ought to know everything there is about numbers by now. And of course, we do know that all about prime numbers. We know what prime numbers are. You naturally come, you're breaking numbers up according to multiplication. And so you figure out that every number can be written as a product of prime numbers. Right? You break things up into their atoms in whatever you're doing, and the atoms, in this case, with multiplication of integers, is primes. So you start figuring out what the sequence of primes is, and then you start asking more subtle questions like how quickly does the number of primes grow and so on. But I want to point out, oops. Perfect. Yeah, that's good. Yeah, thank you. I want to point out that even before you get into subtle questions like the prime number theorem, in principle, we know how to factor numbers into prime numbers. Like if I give anybody in this room a number less than 100, or less than 400, say, and ask you, is it prime? You'll be able to do that. You'll just check up to, well, is it divisible by 3? Is it divisible by 5? And so on. You'll be able to do that. And so you might think that if you've got a computer, then you can quickly factorize any number I give you into primes. That is not nearly as true as you think it is. So here's a number. Now, it's a big number, but it's not unimaginably big, right? So, you know, it's written on 5 lines of text there. So it's the number I got off my colleague, James Maynard. So you might think if I copy that into my computer and ask it to factorize it as a product of primes, then in a couple of nanoseconds, it will tell you the answer. That's not true, right? Even factorizing a number of that size is extremely hard. So, and when I say hard, there's actually a $75,000 reward for factoring that number. Well, actually, I made these slides first, I made this slide about 2 years ago, so that might not be true anymore. But at least 2 years ago, there was a $75,000 reward for factoring that number into its primes, right? So even though in principle we know how to do it, in practice, it's a very hard thing to do, to factor a number into primes. And so even in this most primitive of mathematical structures, simple sounding tasks can be much harder than one first imagines. And what's really behind that is the fact that if you've got an n-digit number, so you count the number of digits here, you want to factor it into primes. Well, if you tell me that you factored it into primes and you give me the solution, it's very easy for me to check that you're telling the truth. I just multiply those primes together to make sure I got the number. Right? So that's something where you can check a solution very quickly. Those sort of problems are called NP, the non-deterministic polynomial time. It's an open problem as to whether you can take an n-digit number and whether you can write a program, a computer program, that would factor a number into its prime factors in polynomial time. That's an open problem, the basic problem. And we don't know whether checking a solution in polynomial time is the same as actually constructing a solution in polynomial time. And that's one of these famous $1 million, the dollar sign missing, crucially. That's one of the crucial the $1 million Millennium Prizes. If you can decide that, it's worth $1 million too. But the main point I want to make is not the details of this problem. It's just the fact that simple sounding problems can be much harder than one imagines, and they can really be open problems. So that's hardness. Hardness close at hand. You don't have to think about strange structures in order to find really hard problems. You find them already as something as simple as multiplying whole numbers together. Right. Now, so hardness is perhaps partly a cultural thing, that you can say a problem is hard or not. But most people would agree that Andrew Wiles's proof of Fermat's last thing was really hard. Right? It's one of the great triumphs of 20th century mathematics. But nevertheless, it's a theorem. Right? So Wiles proved that if you take a power that's at least 3, you ask, do there exist integers, whole numbers, none of which are 0, so that x to the n plus y to the n is z to the n, the answer is no. You cannot find whole numbers, x, y, and z, so let's say x to the 5th plus y to the 5th equals z to the 5th. So, okay, everybody, probably you've all heard that, but everyone understand the statement. Right, now, it's a great theorem. But you might ask for something more. You might think, well, in this age of supercomputers, never mind just those equations, the sum of 2 powers equals another power. What if I give you any Diophantine equation? I just wrote this one down randomly. So you take x to some power plus y to some other power plus some products of x and y and z plus some other power of z. I write that down. Let's call it a Diophantine equation, a polynomial equation with integer coefficients. So Wiles's theorem gives you a class of these equations where you can't find integer solutions, right? You can't find x, y, and z to satisfy that. How about that one I've just written down? Right? Does that have a solution? I don't know. I picked those numbers rather arbitrarily. But you might think, well, if Wiles can answer it for that class of problems, might you actually have a better theorem? Might we just be able to write a computer program so that you just feed the computer an equation like that, a small amount of data, and you ask the computer, do there exist integers x, y, and z so that that's true? Right? Perfectly reasonable problem. You can ask ChatGPT. It may or may not lie to you. So you can imagine that rather than just proving it about individual equations, there's just an algorithm that tells you whether there's integer solutions to polynomial equations. That is an undecidable problem. Right? There's a famous theorem of Matiasevich from 1970, answering a problem that Hilbert had asked at the start of the 20th century. And I've tried to choose my words carefully here. Not that does not exist. There cannot exist an algorithm that decides whether or not the Diophantine equation, something like this, has a solution in integers or not. Now, if you never just absorb that statement for a minute, right? I'm not saying that mankind is not yet smart enough, or mankind has not yet built a computer big enough. I'm saying it can't be done. Right? It does not exist an algorithm. There cannot exist an algorithm that given the Diophantine equation, decide whether or not it has an integer solution. And I think absorbing that there are natural problems, I hope you all agree that's a very natural problem, the problem about whole numbers, there are undecidable problems. It's a perfectly well-posed problem, right? So that equation either has integer solutions or it doesn't. It has a simple yes/no answer, one of which is true and one of which is false. Now, for that particular equation, you might be able to solve it, just as Wild did for that equation. But you cannot ever have an algorithm that tells you whether a solution exists. Now, I don't want to leave that as a total mystery. So it sounds philosophical or even quasi-religious to say there cannot exist a solution, right? Oh, sorry, there cannot exist an algorithm. It's actually a very concrete statement about computers. Here's my idea of a computer. I'm not very good with computers, so I still think of this as a... and so Alan Turing told us actually, you can make a model, so a universal model of computation, which enables you to talk about what computers will ever be able to do. So you might as well think of a computer like this. And roughly stated, what's going on is saying you can never write a computer program so that you give it the input of your equation that says yes or no, according to whether there's an integer solution or not. Now, all theorems like this are ultimately reduced by various layers of clever arguments to this theorem, that there exists, this is an even simpler problem, there exist sets of integers, so it will be an infinite list of whole numbers, so there is no algorithm that can determine whether or not an integer belongs to a list S. Now, what can that possibly mean? It means, so I have this collection of integers S that you should think of as the winning numbers to the lottery, and then you come with your ticket and say, is this a winning number? And I'm saying, I'm sorry, I can't tell you. Now, why can't I tell you? Well, it's because, I'm going to state this theorem in a more precise way. Let's go also back to Turing. Let's say a set of integers is recursively enumerable. If there exists a computer, think of that computer or a fancy computer, that can list the integers in the set S, that's fine. That's my list of winning numbers for the lottery, right? The computer will give me the winning list. That's a recursively enumerable set. What's missing is a list of the losing numbers in the lottery. Right? Could it be that you can list all of the winning numbers, but the algorithm for generating the list of winning numbers is so complicated that you can't simultaneously generate a list of the losing numbers? Now, if the numbers came out in increasing order, that would be easy because you just write down the ones that are on the list, but they don't. They come out in some weird order. Right? So could it be that certain sets of integers that can be described by a computer are so complicated that you can't write a list of the numbers that aren't in the set? And once you've absorbed the fact that that's a real question, it's actually not terribly hard. You can teach it to any undergraduate to prove actually there do indeed exist recursively enumerable sets where you can list all the winning numbers, but you can't list the losing numbers. Which is what I said. You asked me, is your ticket a winner or a loser? At no finite time will you know if you've lost. And so that's an undecidability problem. Right? And again, this is honestly not a difficult theorem to prove. This is the hard and the unknowable now, close at hand. Right? So just literally unknowable. You want to know, does a Diophantine equation have an integer solution? There's no algorithm that will ever be able to tell you. So we go off into the world trying to do mathematics, looking to prove theorems, but always beware that simple problems, simple looking problems can be much harder than you expect. And crucially, things can be undecidable. There can be problems that cannot be algorithmically solved. Right. So let's go back to knots, right? So here's an even bigger knot table. It goes up to 9. Oh, these are all the knots up to 9 crossings now. Can I go on forever? Right? Can you, in principle, if you give me a number, say 1001, can I make a complete list of all the knots so that when you draw a picture of it, it has at most 1001 crossings, and make a proper list, meaning everything is on the list and nothing is on the list twice? Is that a problem that we can hope to algorithmically solve or not? Right? If you're giving a talk about knots, it's very hard not to say the word knots. So you have to say them. Okay, so that's where we're going, right? So we're going to explore various sorts of mathematics with the aim of solving this problem. Can we classify knots? Is it a decidable problem or not? How hard is it? So we're going to shelve that for a minute, and instead of talking about knots, we're going to talk about groups. And groups are the mathematical structure you look at to groups are the mathematical structure you use to describe symmetry in any context. Okay, and we want to do this as a mathematician in the wild, right? So not going into a classroom to be told how to do mathematics, but being a human being going out into the world to explore it and derive some truth for ourselves. So you've gone out with your notebook to explore the universe, and you've come across this lovely object. And you say, oh, that's nice. And one of the reasons it's nice is because it seems to have attractive symmetries. So what notes am I going to make in my diary about what its symmetries are? Well, primitively, as we're discussing, you count. So you might say it's got 6 symmetries. And if you come across this object, model of methane molecule, you can convince yourself that's also got 6 symmetries. There are 6 operations I can do to it that take it back to so it still looks the same. But there's a difference, right? So I note it's true they've both got 6 symmetries, but here there's one basic operation I can do. I can rotate it through one click. So if I do that repeatedly, that will give me all the symmetries. And if I rotate it through 6 clicks, I'll get back to where I started from. Okay? If I stare at that and I say, well, is that also true there? Can I find one symmetry so if I do it repeatedly, I'll get all the other symmetries? And you convince yourself there isn't. You seem to need to do 2 things. You can twiddle it, you can get hold of it and just turn it through a third of a turn, or you could flip it. You can take the 2 big ones and swap them. Big ones is a technical word for a carbon atom, right? So, and so you seem to need 2 basic operations, one of which if you do 3 times, you get back to where you started from, one of which if you do twice, you get back to where you started from. And you might also notice if you flip it and then twist and then flip it again, that's the same as if you twist it in the opposite direction. They're just some notes, right? So you've made some notes in your diary about the symmetries of these lovely objects you found one day. There's the same thing. You might continue on your walk, you come across another item, 3 balls lying there, and you think, okay, how many ways can I rearrange those balls? You realize there are 6 ways. So again, it has 6 symmetries. If I call alpha the operation of flipping those 2 and leaving that one alone, and beta the operation of flipping those 2 and leaving that one alone, then you can convince yourself the 6 symmetries are do nothing, do the alpha, the beta, or alpha and beta, or do them in the opposite order. And then you might notice if I do alpha, then beta, then alpha, it's the same as if I did beta, then alpha, then beta. So you make these notes in your diary. And again, it doesn't really look like that, but there are 6 things. In fact, this group is the same as that group, but it just hasn't appeared in the same way. So now I have to think about what I mean when I say that is the same as that group. It's group symmetries of different objects. What do I mean by the same? Well, this is when I was counting and I said 2 is the common essence of pairs. I now need a new language that isn't counting that will let me describe the symmetries of everything. And I was sort of drawn into making these notes in my diary. Okay, well, I'll have to make sense of that when I get home. Right? So we'll go home, we'll have a cup of tea, and we'll think about how we can properly describe symmetries and what did I really mean when I was making these notes for myself in my diary. And so the language we're going to come to is that of groups. So a group is a collection of things, operations, symmetries that we were doing when we came across those objects in the wild. And it can be symmetries of anything. Right? We had 3 very different contexts. So it's a group of operations, a collection of operations that you do. And what are the crucial factors? Well, you can compose it, right? If you do one symmetry and you've got another symmetry, you can do this one and then that one. And the fact it's a symmetry means you didn't break it, right? You can put it back before your mother finds out. So everything can be undone. Everything has an inverse. And that's probably all you really need to know. There's always an operation of doing nothing. And if you've got two symmetries, you can always do A then B. And you can always undo what you did. And that's it. That's the essence of symmetry. And there's some other little axioms that go with it. Basically, that's the language you're going to need for symmetries. Right? And then what does it mean for two groups to be the same? Well, just like when I had a pair of chairs and a pair of apples, what was 2? Well, 2 was really the act of saying, well, I can match one of those apples with that chair and one of those apples with the other chair. So I've got some sort of mapping, some sort of dynamic thing that says that 2, there's some operation of counting that says these things are the same. So we want some way of matching up the symmetries in the first group with the symmetries in the second group, except now we're not just counting anymore, right? So we have to remember we're doing symmetries. So it should be true that, you know, if I really want to say these groups are the same, then undoing A1 should be the same as undoing B1, so that this matching up process should match up inverses, as they're called, and it should match up the operation of doing one after the other. So that's the natural notion of groups being the same. You should be able to match them up so that you preserve the essence of the thing. And that brings us to the idea of isomorphism, groups being the same. But the point is, you know, we've got to convey information quickly to undergraduates. We package it all up into dense definitions and start with the definition. But mathematics emerges from the truth of what's around us, right? And hopefully, this little argument makes you think, well, symmetries, yeah, groups is the natural way to describe it. This is the natural way to say that two groups are the same. And so just going back, so those two groups are the same. If you've never seen it, it's a nice exercise. Find a correspondence between those two groups. Right, now, but that still doesn't explain these notes I was making in my diary, right? But here I sort of wrote in my diary these key observations about the two basic operations and some equations involving them. So what was I really trying to say to myself when I wrote that information down? Well, I was saying that I'd noticed there were some basic operations, my twiddle and my flip, so that every other operation can just be got by doing a combination of those. So there's some sort of natural thing to call those things generators, right? There's some basic moves I can do. Like if you want to move around in 2 dimensions, there's 2 basic moves you can do. You can move forwards, then there's the inverse moving backwards, so you can move to your left with the inverse operation moving to your right. And all you need is those 2 basic operations to move anywhere in the plane. So that's the idea of generators. You look for basic, you know, this idea of breaking things into its atomic form always. You look for basic operations, so everything else, all the symmetries of the situation, can be obtained by doing these basic ones. So the first assertion is that I found some collection of basic operations. So the whole group, all of the symmetries, can be obtained by doing combinations of those repeatedly or inverted. And then I made some observations about the way these generators interact. And then I stopped. Now, why was I allowed to stop? Well, I was really making an assertion implicitly that all relations, all equations involving the generators follow from the ones I've already written down. Now, right, so I only wrote down 3 equalities in that case. And there's various other equations I could have written down. But the claim is that everything else is an obvious consequence of the ones I've written. Now, what's obvious? Well, obvious means if I've said R equals S and T equals U, then so doing R is the same as doing S. Doing T is the same as doing U. So if I do R then T, it's the same as doing S and then U. Right? So that's an obvious consequence of that. If I know that doing certain sequence of operations gets me back to where I started from, that's called a relation, then if the religious point here as to whether you read this from right to left or left to right. I'm not going to enter that debate. Let me read it from left to right. So if let me read it from right to left. If you do operation A, then you do nothing, then you undo operation A, that's surely the same as doing nothing. Right? So that's an obvious consequence. And the claim is that the implicit claim when you write something like that is you've got all of the information you need about the symmetries of the situation. Okay, so here's a nice example. Imagine this tiling of the plane going on forever, right? And then ask yourself, what are all the symmetries of it? Well, there's some obvious things, like you can just take it and shift it along by 1 square, or I can shift it up by 1 square. But I'm not going to use those as my basic operations. what I'm going to use as my basic operations is I'm going to focus on one triangle in this picture and observe that if I rotate, so that pink triangle goes to the next one, that extends to a symmetry of the whole tiling, the whole paving. Okay? And how many times do I have to do it to get back to the origin, to get back to the identity? 1, 2, 3, 4, 5, 6. So there'll be a rotation, which I've called C. So if you do it 6 times, you get back to doing nothing. If I rotate about the other 2 vertices in this triangle, right, then one of them I only have to do twice, that's A, and one of them I have to do 3 times, that's B. And then I claim, and it's a theorem now, right, that you can try and prove for yourself, you really can try and prove it for yourself, that every symmetry of this picture, of the infinite paving, can be obtained by doing a suitable combination of A, B, and C. So if you want to, for example, translate the picture over 2 steps, just translate it over 1 step, then you must be able to write a combination of those A, B, and C rotations to do it. And the claim is that this is all you need to know to figure out all of the equations between A, B, and C. Okay, so we have this concise language for expressing the symmetries of infinite objects. And it's an infinite group of symmetries, obviously. Right, now, when we started counting, first of all, we had this efficient way of figuring out what all pairs have in common. But then we started doing operations, right? We started adding numbers. And then you start doing number theory, beautiful subject, where you start inquiring about the properties of numbers. So now we're going to do group theory. We're going to start inquiring about the property of groups. So one thing we might do is just write down a group. Since we have a language for describing groups, I might just write down a language of a group and then say, well, what's it the symmetries of? Right? So you can write down an algebraic description, and then it ought to be the symmetries of something. What is it? So I'm going to take this group, and I'm going to say, well, the numbers 2, 3, and 6 are all very well, but suppose I replace it by some other numbers. Suppose I replace the 2, 3, and 6 by 3, 3, and 4, for example. Then can I find some object whose symmetries are exactly that expression? Has everyone got the game? So here, we started with a well-known Euclidean object, and we worked out what its symmetries are. Now, we do what's often fruitful in mathematics. We go the other way. We write down an algebraic expression, and we ask what's the symmetries of. We're going the other way, description to the object. And guided by the Euclidean situation, we might start trying to stick triangles together so that the number of vertices, the number of triangles that meet at each vertex in this picture correspond to these numbers I've written down here. And you get this. And now I can't fit it in Euclidean space, right? It sort of buckles up. But nevertheless, I can draw this picture. And if you just imagine it's a very flexible picture and they're made of rubber, these triangles. So I can still, if I try and rotate here, everything will move around in a nice flexible way. I've discovered this object that has the right symmetries. But now we look at that and we think, well, what have we discovered? What sort of object is that? So the Euclidean picture of it doesn't seem quite right, because yes, it feels like if it's flexible, I can make these moves, but I'd like to have some notion of distance and angle and be able to do geometry in that space. And so what sort of geometry have I discovered? Well, what we've discovered by this trying to think of symmetries is we've discovered what's called hyperbolic geometry. Okay? Now, roughly speaking, what you do is you look at this picture and you say, well, I want to think of it as a geometric object, so I shall just declare by fiat that all of the edges in this picture have length 1. And that's given me a new notion of distance, right? So it's like a road system. You want to go from there to there, you just have to count how many edges they have to go across. I've created a new geometric object. Okay, but I've created, does it exist in nature? Well, it actually, sorry, I meant to say, it's really very different. This is what's called hyperbolic geometry. Never come across it, explore it. It's an absolutely beautiful thing, right? It puzzled the ancients as to whether this existed, and this wasn't really settled until the 19th century, even though we've just seen sort of very concrete model of it. But when you live in this space, if you sort of ask yourself, what's it like to live in this space? Well, it feels very curved. Everywhere you feel like you're at the apex of a saddle, if you measure a triangle, you draw take 3 points, draw the shortest curves between them, you find they're thin like this, that the angles add up to less than 180 degrees. It grows very quickly. If you try to count, if you try to count the number of triangles within a distance 10 of that central point, for example, in Euclidean space, that would grow quadratically with the radius. In hyperbolic space, it grows exponentially. You get a lot of volume or area very, very quickly. So you don't want a house in hyperbolic space because you couldn't afford to heat it or cool it, right? Because the amount of area is absolutely enormous as the radius increases. And for example, if you make a three-dimensional model of this, in order to fit the volume of the Earth in a hemispherical swimming pool, you only need a pool 10 meters in diameter. So just volume grows incredibly quickly in hyperbolic space. There it is. It's a beautiful object. And does it exist in nature? Well, patches of it do, right? You find hyperbolic vegetables. There's lots of vegetables. Whenever you have a splitting process, it's trying to grow exponentially. So there are lots of hyperbolic vegetables in the market. There are lots of hyperbolic organisms, right? There's lots of corals that sort of grow. So if you try to flatten them out, the geometry of it is exactly the geometry of the hyperbolic plane. There are even people you can find on the internet who try to knit hyperbolic clothing using a lot of fabric. And it exists in every dimension, okay? So I did it in dimension 2, but then one can ask, is there a model of this hyperbolic geometry in every dimension, just as we imagine Euclidean space existing in every dimension? The answer is yes. In particular, we have this sense of Euclidean space that we think we live in. One can make a hyperbolic space. Now, I said the Euclidean space that we think we live in. Are you sure you live in Euclidean space? Right? So we laugh at our ancestors for thinking they lived on a flat plane. But was that such a stupid idea? Right? They could draw a square around themselves and they could pile squares up forwards and backwards and sideways direction. And then locally, their Earth looks like it's flat. So did they live just on a plane that went forever? I say, of course not. But then, don't we make the same mistake in three-dimensional space? We live in a box like this room, and you stack them up and down and to the sides and that way, and you make a three-dimensional stack. And you imagine that's what three-dimensional space looks like. But how do you know that? And maybe you actually live in a model more like hyperbolic space. That's an idea we're going to come back to. Okay? The symmetries of space. Okay, right. We had so much fun with that. I must admit that. How much time do I have left? I don't know. Sorry? Oh, right. We had so much fun sort of making hyperbolic space. Let's make another one. Here's another group of symmetries, 3 generators, few relations. Is that the symmetries of a beautiful object? Well, it worked pretty well last time. Hands up if you think that's the symmetries of a beautiful object. Hands up if you think it's not. Oh, come on. Okay, right. I'm lying to you. Well, it depends whether you think a point is a beautiful object or not. That is actually the trivial group, by which I mean that from those rules written there, you can deduce that A, B, and C are all the operation of doing nothing. And therefore, that is the thing that says something has no symmetries. Now, if you voted the wrong way there, don't worry. There's nothing algorithmic you could have done to get the right question, to get the right answer. Right? That this is like those undecidability problems that we quickly came across before. Deciding if that's the trivial group or not, you can't do that algorithmically. Right? Deciding whether a group of symmetries that I give you is non-trivial or not is something that can't be done algorithmically. The first person to realize this was this Max Dane in the year this photograph was taken. He was the first person to think seriously about whether group presentations really describe as much information as one hopes they do. Right? How hard is it to decide what you've got when what you really know is the symmetries of it? So, for example, he asked, And this was before computers, right? So he asked, do there exist algorithms that allow us to answer basic questions such as, is the group I've given you, for example, that one, is it a trivial group or not? Or is it a finite group or is it an infinite group? Or whether certain equations in the generators are true or not. And the thing I want to concentrate on now is why he cared. And he cared because of this. One is led to such problems by necessity when working in geometry and topology. Knotted space curves, which we want to classify, in order to be completely understood, demand the solution of these algebraic problems. So here we are. So the problem of deciding what sort of symmetries we've got, it's about to collide with our problem of deciding which space we're looking at. So once again, he's trying to make knot tables, work out what all the knots are. And I'll tell you how he was approaching that and why he got interested in groups. But first, let me tell you this. So that what I said about don't worry if you couldn't guess what that group was, there's no algorithm you could do. So this was one of the great achievements of group theory in the middle of the 20th century, mostly by the Russian school. That for finitely presented groups, that is groups given with a finite number of generators and a finite number of rules, there is no algorithm that in general will let you tell whether the group is finite or trivial or infinite, or whether a particular product of the generators is the identity or not. There are no algorithms. It's a hopelessly difficult, unsolvable problem. But, so that's mathematics up to the 1950s. This is what happened up to about 2005. And this is the whole of the program of understanding three-dimensional spaces goes into this. So the groups that arise in knot theory, in trying to classify knots, and in trying to understand what universe we live in, what three-dimensional geometries can be, there do exist algorithms that will solve all the problems you can ask about a group that arises in that second. Okay? So let me pause on this again. So for groups in general, there are no algorithms. But for groups that arise in two-dimensional geometry and topology, there are algorithms. So we want to think about why, right? So there's something special about the dimension in which we appear to live, 3 dimensions. And it's much of this difference is could do with the geometry of this 3-dimensional hyperbolic space that we just encountered. And the knot that I want you to think about is the figure 8 knot. Okay, so we can see a special property of the figure 8 knot, which is going to connect to hyperbolic geometry groups. So we're trying to classify all knots. We've got lists like this. We'd like to go further. If I had more time, I got. So this is Lewis Carroll, who wrote Alice in Wonderland. He used to talk a lot about knots, but he also used the word knot to mean any hard problem. And he wrote these wonderful articles about tangled tales and knots. That's a complete tangent, I'd say. Let's go back to the figure 8 knot. So I'm going to tell you, more or less implied, that there are ways to classify all knots, right? You can make these knot tables go on forever knowing exactly what you've got. But let me once again pause to say life is hard. That really honestly is a picture. So that if you take that piece of string and you tug it around, you'll find it's the unknot, or the knot knot. That's another one. That's a picture drawn by a German mathematician, Wolfgang Haken. That's honestly a picture that if you tug it, you'll get to that. But how are you going to stare at that or start playing with it and know? That's the difficulty. Right? So what can you say that's systematic? What can you do algorithmically to decide that that really is the unknown? Okay, now the first person to make serious progress on that is that guy there. Now you can see he's not very happy. That's because he was living in Scotland in the 19th century where it was very cold and wet. That is P.G. Tate. And without warmth or television in the evenings, he decided to make knot tables. He had other motivations as well, but he made tremendous progress on making knot tables more or less up as far as this, and making incredibly few mistakes. Okay, but then let's try and be a bit more systematic about it. Let's try and do some modern mathematics. First of all, we need to know what we mean by a knot. I think we've decided, right? It's a map of a circle into 3-dimensional space, which is an idealization of a piece of string. I think we've decided we have to be careful. What do we mean for knots to be the same? Well, you've got to tug it around until they really look the same. you have to make that precise, right? But you just really honestly think about the mathematics that makes that notion of tugging it around without tearing it precise. That's a notion called isotopy. And then we want methods, but we want them to be algorithms, right? We want to be able to convey to our fellow humans what it is that you have to do to tell whether two knots are the same or not. You don't want to rely on luck. You want to have some algorithm to decide if two knots are the same or not. And if this is going to work, now, since we don't live in Edinburgh in the 19th century and we'd like to get beyond 9 crossings, we're going to have to think about what sort of mathematics we can bring to bear, what sort of power of modern mathematics can we use to gain more insight into this problem. And just to say that this is obviously a natural problem that lots of people have thought about, Alan Turing himself actually used this as one of the sort of, when he first started thinking about unsolvable problems, for him, this was one of the sort of beacon problems. In this famous article from 1954, he notes that no systematic method is yet known by which you can tell if two knots are the same or not. So it's a problem that's come up throughout history. Right. Now I'm going to go back to Max Dane, and in the couple of minutes that remain, explain why I was talking about groups and then knots. And this isn't the way Max Dane phrased it, but I can't resist this. He proved a theorem. Well, he thought he'd proved a theorem. He actually made a mistake, famously, and it wasn't fixed until the 1960s. But nevertheless, the theorem is true. That is also, for the younger people in the audience, that is also, everybody makes mistakes. Right? So having the right intuition and honestly trying to prove theorems is something you do, and you should not be afraid if occasionally you make a mistake. Right? Even the greats, including Max Dane, made a mistake that wasn't fixed for 50 years. So if a knot is not the knot, then the group of the knot is not the knot group. That's not exactly how he phrased it, but it is nevertheless true. It's written out in symbols here. I'm going to describe a group to you, which is this thing, and say it's the same as the group of integers under addition, if and only if the knot is the unknot. It's the knot. So that's why I'm calling it the knot and not the unknot. A knot is not the knot, then the group of the knot is not the knot group. Okay. Now, why does that solve our problem? Well, there's some beautiful theorems that were proved towards the end of the 20th century, including this one by Gordon and Lukey. If you're going to solve the problem of this depth, you need a change of perspective. And now this might seem like a trivial change of perspective, but it's actually very important. Instead of thinking about the knot, you think about what's not in the knot. That is, you drill out the knot. Right? You drill out the knot, and you think about the space that's left outside the knot. And then when you think carefully about it, it's not obvious that if I take two different knots and drill out, that maybe the outsides are the same, even though the knots were different. There's a wonderful theorem of Gordon and Lukey that essentially says that's not true. But it's a highly non-trivial fact. If the outsides of the knots are the same, then the knots themselves are the same. Now, why does that help us? Because with the outside of the knot is a space that has more substance to it than just this piece of string. And in particular, this is where the groups come in. And this is a great idea of Henri Poincaré at the end of the 19th century. He associated a group to any space. And it's so important, it's called the fundamental group. It's always written like that. And roughly what's going on here is you take a knot, you think about what's outside the knot instead of thinking the knot itself, and then you take this group that Poincaré gives you. And so this is not quite what Gordon and Lukey said, but roughly speaking, you take the knot and it's uniquely determined by the group. Right? So you go from knots to groups, and it's a faithful encoding of the problem. That two knots are the same, two groups will be the same. If two knots are different, the groups will be different. There's some technicalities here, but we're not going to worry about them. We're instead going to think about what the outside of a knot might look like. Right? So the outside of the knot is some three-dimensional space. You wander around in it, right? The knot's here, deleted. I'm wandering around in this space. I want to know what is the natural geometry of this space. So, well, what are all the possibilities? Can we classify all the possible reasonable models of three-dimensional space and then apply what we've learned to the spaces that we get by drilling out these knots? Okay. We're going to warm up in 2 dimensions, and I'm going to go back to everybody under the age of 20 should know you should never trust anybody over the age of 20. So when people tell you the Earth is flat, maybe they're lying. Maybe it's actually like the surface of a big donut, or maybe it's just flat. Right? Try and get a group of you together and think of an experiment that young people can do to prove that the old people really are telling the truth and you really live on a sphere. If you get enough young people in the world together, you should be able to think of an experiment to prove you live on a sphere without having to leave it and take photographs in space. Nevertheless, there are different possible models, right? We're going to do this. You could also live on the surface of a 2-handled donut like that, or you could keep going. You know, maybe it's a knotted surface like that, but you can figure out that actually you can make a complete list of all the possible surfaces that you might live on, all the possible models for 2-dimensional space, at least the ones that are compact, at least the ones that have a finite amount of area. And we'd like to do the same thing in higher dimensions, right? That's what we'd like to do in 3 dimensions, make a list of all the possible models of 3-dimensional space, maybe all the ones with finite volume. But I said geometry, not just shape, and I don't want these things to be made of rubber. And an amazing thing in dimension 2 is that on each of these surfaces, just as we did with the hyperbolic disk, where we said, well, you know, I've got this rubbery object, but is there a way to make it so I can really measure distances and angles on it? You can always do that on a surface. And you'll either have flat geometry, the one that we're used to, or the round geometry of the Earth, or this hyperbolic geometry that we encountered earlier. All models of 2-dimensional space, you can rigidify them so they have one of those geometries. Might that be true in every dimension? It might be true you can always get on any reasonable model of space in any dimension, there's always a natural geometry. That was Bill Thurston's version. That's Bill in the middle. That's Henri Poincaré, who we're discussing on the left. That's Perelman, who solved the Poincaré conjecture on the right. And Thurston's vision was essentially, it's not true that every 3-dimensional space has a natural geometry in the sense of 2 dimensions. It's just not true. It was a dream, doesn't work. But what Bill realized is that there are really only 8 reasonable models for what a 3-dimensional geometry might look like. And whilst it's not true that every model of space has one of those geometries, what is true is there's a canonical way to cut it up into pieces, so each of the pieces has that geometry. Now, I said that very quickly. But there's good news and bad news. The bad news is not everything has a natural geometry. The good news is you only have to make a finite number of cuts, and then it falls into pieces, all of which have geometry. That was the overwhelmingly most common geometry is the hyperbolic geometry. If you take a generic model of 3-dimensional space, it will have hyperbolic geometry. For example, the outside of the figure 8 knot, when you straighten it all out, as we did with the triangulation of the plane, its geometry on the outside of that knot will feel like that. When you're wandering around on the outside of this knot, once you've straightened it so you can do geometry, it will feel like you're wandering around in that hyperbolic space. And because we understand, there's some other models that are much more tightly wound than that hyperbolic space. But the key fact is that because we can understand all geometries of 3-dimensional spaces, we can understand all geometries of the outsides of knots, which means we can understand all knots. And that is why we can classify knots, right? By going through these 3 manifold geometries and describing them using their symmetries, using groups. And finally, I'd like to go back to the idea of, well, it works so well in dimension 3. How about going to dimension 4 and 5 and 6 and keeping going? Groups tell you it's too hard. And I don't mean it's just too hard to think about what 4 dimensions looks like. These guys, Novikov and Markov, prove that there's no algorithm that can decide whether different compact models of space are the same or different once you get to dimension 4 and above. Right? There is no possible way that you can classify higher dimensional models of space as we did in dimensions 2 and 3. And it's because you can faithfully encode all groups into models of space above dimension 3. And since you can't understand what groups are, you can't understand what the models of space are. It genuinely becomes an undecidable problem. Not just we haven't done it yet, it's undecidable. Thank you.
Thank you for the very engaging talk. So we'll take questions from the audience now.
Thank you for the amazing talk. So I wanted to ask you that, so you have classified the knots up to for which is embedded in the R3 itself. So what if it's embedded in the torus in genus? So is there any classification for that or is it the same classification?
Sorry, say that again.
So if the knots are embedded in the torus in genus surface, okay, is there any classifications for that?
You mean if I've got
Yeah,
so
suppose
if I'm knotting surfaces instead of a torus?
yes.
People have worked on that, but I don't think they're classified. But in principle, one could do it because in the same way that I've described this program, that you can think about their exteriors and classify their geometries and the certain groups, but there are elements missing that I'm not sure of. Like there's this theorem I mentioned of Gordon and Luckey that said that when the outside of two knots are the same, then the knots are the same. And one would have to prove that embeddings of higher genus surfaces, and I'm not sure if that's true or not.
Okay, thank you. And one more question. So you have told that when you have the knots, like for the embedded in R3 itself, so for 7 knots, there are at least, I think, 6 or 7 models are there. And for n numbers, so is there any relation between if you have a n knots and its prime factorization, it's U1, P2, Pn to the power some R, and how many ways you can get it the n knots with the n prime factorization? So is there any relation between the prime factorization of the number n and how many models you can construct with the n knots?
I see. Not a simple relation. No, not a simple. So, for example, I said that hyperbolic geometry is generic. If you write down a knot with lots of crossings and you don't try to do anything clever, then the outside will always just have a pure hyperbolic geometry, no matter how many crossings you have. So generically, you expect knots to have hyperbolic outsides, hyperbolic exteriors.
Any other questions? So for the decidability, you have like a classical computer where things take 0, 1. Does the question make sense for quantum?
Oh, that's a good question. Yeah, so I'm not an expert on quantum computing, right? So there's 2 things that one might ask in modern era, right? So quantum computers or AI. Quantum computers is much the better question. My understanding is that you can speed things up, right? But it's not clear you can do anything new. So it'll change the computational complexity class about what's polynomial and what's not, for example. But if things can't be done on a classical machine, it can't be done on a quantum computer either. It's my understanding, but I'm not an expert. What you can do is think about probabilistic proofs. Can I prove something with arbitrarily high probability? But you can't. If something cannot be settled yes, no, with proof on a classical computer, then it can't be done on a quantum computer either.
Hi, thanks very much. I was just wondering, since you mentioned at the beginning the fact that there's no Matiasevich's proof that there's no algorithm to decide whether Diophantine equations have solutions or not, and then the similar result for the group, the finite group presentations. Is the nature of proving it similar, or are they very different kind of?
That's a good question. So there are different proofs of both theorems. That's celebrated theorems. But in the end, most undecidability results are proved by saying, I'll prove my problem reduces to another problem which is already known to be undecidable. And in that sense, both proofs, or all the proofs, go back to this fact that I concentrate on at the beginning about being sets of integers where you can't decide membership. That's the basic ingredient in everything. And in particular, that's the basic ingredient in both Matiasevich's theorem and the theorem about proofs. you encode it in different ways, but it's always encoding that basic fact.
I just wanted to go back to that question of quantum versus classical. And what you say is quite true. It's quite easy to prove that any quantum algorithm can always be implemented as a classical computing algorithm. So if you can't do something on a classical computer, you can't do it.
I'm glad I got that right. Thank you. Tell us a little bit.
Thank you for the wonderful talk. Do we have any sense of how the number of unique knots up to how we defined uniqueness, how it grows asymptotically?
Yeah, no, so this isn't, I'm not, that's not a subject I've thought about, but yes, you can make quite naive estimates, just by sort of graph counting. Just think about the picture of the knot and think about how many possible pictures there are. But then, as your question implies, it's a much more subtle question to say how many different ones there are and how many are the same. And that's quite a hard problem, I believe, is to get reasonable estimates, reasonable lower bounds.
Thank you.
Can you just explain us the applications of knot theory in space sciences?
In what?
In the applications of knot theory in space sciences, where it is applicable in space.
In space?
Or a three-dimension space.
What do you mean by applications? You mean, so there's various other mathematical problems you can encode into knot theory. I rather like applications in a more sort of hard science sense. That I showed this picture at the beginning of a trefoil knot that actually appears in some knotted DNA. There's some very interesting work on connected to protein folding about how the knottedness of chain molecules, for example, affects their chemical properties. And the reason I like it is because, well, the knottedness really matters. And so the invariants that you would use to study knots actually have real physical meaning in knot application. So I think the one I know of that I think is most interesting is in biology. I might say, so Tate, who I was sort of making fun of for that picture, he originally started making these knot tables because Thomson had a theory of vortices as the fabric of real space. And the question arose then what vortices are possible? And the physicists in the late 19th century were very interested in classifying knots as part of this theory of vortices. So Tate himself really, that was his motivation, trying to classify these knots.
Hello, sir. I just wanted to ask how does studying the outside geometry of a knot really relate to the nature of the knot or the group itself?
Yeah, right. So in the end, there's this theorem, right, that says there's equivalent information in the two things. But somehow, if you're just looking at the piece of string, you're limited in the tools that you have as what to do. But when you get to this space, there's much richer questions you can ask about it somehow. The ways in which you can manipulate it are much greater. And in particular, this fantastic theorem this fantastic program of Thurston of understanding three-dimensional space. You need room to move around and to impose structure on the space. So I'm not explaining it very well, but there's a much richer range of possible things you can do in the outside of the knot than there is just with the knot itself. But once you know, for example, that the outside is hyperbolic, then it tells you lots of things about the knot itself and the group of the knot. So you get a lot of information from the outside about the knot itself.
Maybe we can take more questions quickly. So please join us for tea outside, and then let's thank Professor Bridson again.